So we move on from set theoretic proofs, much to everyone's dismay, because everyone loves set theoretic proofs so much, to talk about relations. So before we get into that, let me just describe carefully in a set theoretic way what an ordered pair is. We're all probably familiar with the idea of an ordered pair from the Cartesian plane. We use them all the time, but we never really define them in terms of what they are as sets. So if we're defining them really carefully, we would say that the ordered pair xy is defined by the following set. So xy consists of a set containing x and then a set containing xy. This is really how we carefully define an ordered pair. Of course, we think of it more as just a list inside of parentheses of two elements where the order matters, right? So we think of the point, let's say 1, 5 on the Cartesian plane as, this represents an x and this represents a y, but if we want to define what this is carefully, it's really a set whose elements are a set containing 1 and then another set containing 1 and 5. So you don't really need to use this definition. It's just good to know that there is a set theoretic definition for these elements. So ordered pairs are technically examples of sets. One important aspect of ordered pairs is that the order does matter. So unless x is equal to y, the ordered pair x comma y is not the same as the ordered pair y comma x. And the reason for that is we can just use a definition. The ordered pair xy is a set whose elements consist of a set containing x and a set containing x and y, while the ordered pair yx would be a set containing just y and a set containing y and x. Right, so this element and this element are the same, but the other elements of these sets are not the same. All right. I felt compelled to tell you this is a definition of an ordered pair, but realistically, this is how we think of them. We think of them as two elements inside a set of parentheses where the order matters. Okay, now, we say that the Cartesian product of sets A and B is just a set of all ordered pairs whose first element comes from the first set and whose second element comes from the second set. So we would write A cross B, that's how we read that, A cross B. It's just a set of all ordered pairs where we choose one element from the first set and one element from the second set. We've seen this, of course. The Cartesian plane is just the Cartesian product of the real numbers cross the real numbers. So for example, you would have the ordered pair 0, 0 is an R cross R, the origin on the Cartesian plane, because 0 is an element of R and 0 is an element of R, but you'd also have points like pi comma square root of 2 is an R cross R, because pi is an element of the real numbers and square root of 2 is an element of the real numbers, etc. All right, let's do another example. So this is a Cartesian product of two finite sets. Let's say big A contains elements little a, little b, little c, and big B contains elements little c, little d. Then the Cartesian product of A cross B is just going to be a set of ordered pairs, and it's all ordered pairs where you choose one element from the first set and then one element from the second set. So this is going to consist of the ordered pair A comma C, A comma D, then B comma C, B comma D, and finally C comma C, C comma D. Okay, so if there's 3 elements in the first set and 2 elements in the second set, then there's going to be 3 times 2 elements in the Cartesian product. So 6 elements in the product, 6 ordered pairs. Now, given a particular Cartesian product, we say that a relation R between two sets A and B is just any subset of A cross B. And if A and B are the same set, then we would say that R is a relation on A. So let's do an example of what this means. So in example 2, this was our set A, this was our set B, and this was our Cartesian product. Now there's many possible relations here. A relation is just a subset of the Cartesian product, so it's some collection of these ordered pairs. So you could have a relation, let me call it R1, which consists of AC, BC, and CC. Right, because that's a subset of A cross B. You could have another relation which just consists of A comma D. Okay, In fact, you could have another relation which is all 6 of these ordered pairs, because that would technically also be a subset of A cross B. These are all relations, right? You could even have the empty set, because remember, the empty set is a subset of every set. Subset of everything, including a subset of A cross B. So these are all examples of relations on A cross B. If it's a relation, just to give an example, let's say we wanted to describe a relation on just the set B. That means it's a relation on B cross B. And that means it's a subset of B cross B. B cross B would be ordered pairs where you choose one element from B and another element from B. So CC, CD, DC, DD. So any subset of this relation or any subset of this Cartesian product would be a relation on B. So for instance, if we define R to be the set containing CC and DD, that's a relation on B cross B. All right. Now, all of this seems like a lot of kind of arbitrary definitions for things, but usually relations are actually describing a relationship. So as an example, consider the set of natural numbers. We can define the relation R as follows by saying that an ordered pair x comma y is an element of R if and only if x is less than y. So in this case, the relation is just describing the less than relationship. So for instance, any ordered pair where the first element is less than the second element and they both come from n is going to be in this relation. So we could say 1 comma 2 is an element of this relation. 2 comma 3 is an element of the relation. We could say 1 comma 3 is an element of the relation. But 2 comma 1 is not an element of the relation because 2 is not less than 1. Okay, but any pair of natural numbers where the first one is less than the second one would be in this relation, and we would say that it satisfies the relation. One other notational thing, sometimes we would write, instead of writing x comma y is an element of R, sometimes for shorthand we just write x, R, y. This is just a shorthand way of saying this. So for all of these relationships down here that we had, we could write as shorthand, 1 relates to 2, 2 relates to 3, 1 relates to 3, etc. This just means 1's less than 2, 2's less than 3, 1's less than 3. All right, let's look at another example. This time, we're going to let X be the set of all people, and we're going to let A be the set of all movies. Then we're going to define a movie relation called M on the set X cross A. Okay, keep in mind, X cross A is the set of all people crossed with the set of all movies. So this is ordered pairs of person comma movie. And we're going to define this relation by saying X comma A is an element of M if and only if person X has seen movie A. Right? So for instance, you could say Shelley, comma, Cats is an element of M because, alas, I have seen the movie Cats. I'm the only one, so if you just chose another arbitrary name, anyone that's not me, I'm just going to choose the name John. John, comma, Cats is not in M because no one else saw the movie Cats except for me. So I can conclude that John, comma, Cats is not in this relationship, but any movie that you've seen, you, comma, a movie you've seen. All right, what's a movie everyone has seen? Probably Jurassic Park. I'm going to assume you've seen Jurassic Park. You, comma, Jurassic Park would satisfy this relation if you have seen Jurassic Park. All right, just another example of a relation, right? Relations can describe relationships between numbers, but also between other things as well. Now let's look at example 5. If X is still the set of all people, we can define the relation P on X. Okay, so P on X means our ordered pairs are going to be people and people by saying that X comma Y is in P if X is a parent of Y. Right? So I could say, I'm going to utilize my sister here, Jackie, comma, John satisfies this relation P because my sister Jackie is the parent of my nephew John. Okay? Or, you know, your mom comma, you are going to be in this relation because your mom is the parent of you. Okay, but for two people that are not related, let's say me and you, me, Shelley, and you, the viewer, I am not your parent, so this does not satisfy this relation. All right, so we've seen some examples of relations. In the next video, we'll talk about some special properties that relations can have. In particular, we'll talk about equivalence relations.